Note that some whole numbers have many divisors. For example, the divisors of 12 are, but other numbers have fewer divisors. The divisors of 15 are, and a useful idea when doing mathematical research, go to extremes. Every number has divisors of 1 and n, so the extreme case is when these are the only divisors, and this motivates the definition of prime number. A whole number greater than 1 is prime if it has no divisors besides 1 and n. At the same time, we can introduce the idea of a composite number. A whole number n greater than 1 is composite if it has divisors besides 1 and n. Note that 1 is neither prime nor composite. We say that 1 is a unit. For example, we can categorize as prime or composite, then, importantly, prove. 6 is composite, since it has divisors 1, 2, 3, and 6. And as a proof, we can write 6 as a product, and so 2 divides 6, and 3 divides 6. Meanwhile, 5 is prime since it has no divisors besides 1 and 5. And this does actually require proof. We need to show that 2 doesn't divide 5, 3 doesn't divide 5, and 4 doesn't divide 5. And note that it's actually very hard to prove that a number is prime. For example, we want to show that 827 is prime, or is it? This motivates a different definition of prime. A prime number is a whole number greater than 1 that cannot be written as a product of two smaller whole numbers, and again, the corresponding definition of composite number is something that can be. So we can take a look at the product of all numbers smaller than 5, and we find, so 5 cannot be written as the product of smaller numbers, so it's prime. And again, another good strategy for research. You've done the work. You might as well take credit. Notice that this also proves that 4, 6, and 8 are all composite numbers because we've written them as the product of smaller numbers. Now, this leads to an important idea in mathematics. In mathematics, definitions are accepted, while theorems must be proven. But every definition is a biconditional. It's an if and only if statement. So they all look like something that can be proven. In general, we might be able to prove that two definitions are equivalent if we can prove the first definition, which is accepted, can be used to prove the biconditional corresponding to the second definition, and conversely. In other words, we can prove a biconditional. So we have two definitions of prime. Let's prove that the two definitions are equivalent. So first we want to prove the first definition allows us to prove the second written as a biconditional. So we'll assume the first definition. The second definition corresponds to the biconditional. A whole number greater than 1 is prime if and only if it cannot be written as a product of smaller numbers. Rewriting this as two conditionals, if a number greater than 1 is prime, then it cannot be written as a product of smaller numbers. And if a number greater than 1 cannot be written as a product of smaller numbers, then it's prime. So let's try and prove these. Remember, you can always assume the antecedent of a conditional. So suppose a number n greater than 1 is prime. By the definition we're using, it has no divisors besides 1 and itself. We'll use proof by contradiction. Suppose n can be written as a product of smaller numbers, so n is pq with p and q both less than n. But p is a divisor of n that's not n or 1, which is a contradiction because remember, n was supposed to be prime and had no divisors besides n or 1. So n cannot be written as a product of smaller numbers, which proves one direction of the conditional. Now we want to go in the other direction. Suppose n cannot be written as a product of smaller numbers. So we know that any whole number n does have divisors 1 and n. If n has another divisor p, then n has to be p times q. But if p isn't 1 or n, then neither is q, and so n can be written as a product of smaller numbers. So n can't have divisors besides 1 and n, so n is prime. And that gives us the other direction of the conditional. So if we use the first definition of prime, we can prove the theorem, let n be a whole number greater than 1, n is prime if and only if it cannot be written as a product of smaller numbers. And so this means the standard definition of prime implies the alternate definition. Now suppose we use the alternate definition of prime. The first definition corresponds to the biconditional. If a number is prime, then its only divisors are 1 and itself, and if the only divisors of a number are 1 and itself, then the number is prime. By our second definition, a prime cannot be written as a product of smaller numbers. So again, we'll use proof by contradiction. Suppose n is prime, but it has divisors p other than 1 and n. So n is pq. So n can be written as a product of smaller numbers, but by the definition we're using, n can't be prime, and since it is, it can't have divisors other than 1 or n. Now suppose the only divisors of n are 1 and n. If n isn't prime, we can write it as a product of smaller numbers, but this would give it additional divisors, so n can't be prime, which is a contradiction. So if we use the second definition of prime, we can prove as a theorem, let n be a whole number greater than 1, n is prime if and only if its divisors are 1 and n. Since either definition allows us to prove the other as a theorem, the definitions are equivalent. So we can use one and introduce the other as a theorem. In practice, the first definition is the standard definition for primes. But in actual research, it's common to show that two seemingly different concepts are in fact equivalent definitions of the same object.